Hello and welcome back to Database Management Systems. And once again, we are going to continue from the previous video where I explained these extraneous attributes, the two rules that can be applied for finding extraneous attributes and removing them to calculate canonical covers. And I also showed you how to find the canonical cover by applying Armstrong's axioms in the previous video. And this method that I'm showing right now is a sort of a shortcut of that previous method. And let's quickly talk about the two rules that we have, which are here. These are the two rules. Here you have an attribute. This first rule talks about an extra attribute on the left side. So if this is an extra attribute on the left side, and you remove it, and you remove the original dependency from F, which is a set of functional dependencies, and add this new dependency where the attribute small a is removed from the left side. And still, whatever was your original set of dependencies, you can still generate those logically by applying Armstrong's axioms. Then that means this was indeed an extra attribute and you can remove it. And same way, the second rule applies to the right side instead of the left side. So here in this case, on the right hand side, small a is extra. And so you are removing the original dependency, but you are adding this new one where from the right side you have removed this extra attribute. Then once again, you can generate the original dependencies without worrying about having removed this extra attribute. So these are the two rules for extraneous attributes. And now we are going to try to solve a question of finding canonical cover by using these two rules. So this is the relation that we are going to use. It is called relation R, and it contains 4 columns W, X, Y, Z. And the functional dependencies present here are X determines W, W to Z determines XY, Y determines W, X, Z, and what we are supposed to do is find the canonical cover for this. So I'm going to begin, first of all, by applying the decomposition rule on all these dependencies because that is absolutely necessary no matter what you're trying to do. Decomposition is necessary because you can see in the second dependency, there are 2 attributes on the right side. Here there are 3. So it's actually not 2 dependencies, it's actually 5 dependencies all merged in one, all merged in 2. So that's why you need to decompose that. And so I'm going to write all the dependencies again. Here, X determines W is present as it is. WZ determines X. WZ determines Y. Let me also give them numbers so it's easier. Number 4 is Y determines W. Number 5 is Y determines X. And number 6 is Y determines Z. And now what we are going to do is apply all the rules that we have on the right side. So we are talking about the right-hand side of all these dependencies. I'll just write that down here. We are talking about the right-hand side. So we'll begin with the first dependency, which is X determines W. On the right side, there is W. So what we are going to do is calculate the closure of X. Now the closure of X right now is X itself and of course W, and that's it. There's nothing else in the closure of X if you look at all the 6 dependencies we have here. Now, imagine that this dependency which I have written, I'm removing from these 6, and then I'm calculating the closure of X. Now the closure of X would contain X itself, but would it contain W? No. So that means if I remove this dependency completely, then the closure of X is changing. So this dependency is not extraneous. W is not extraneous on the right-hand side, and I have to keep it. So not doing anything for that. Let's check the next dependency, which is WZ determines X. We're going to calculate closure of WZ, which would contain WZ and X. But would it contain anything else due to that? You can go through the list of 6 dependencies that we already have, and you can conclude that it can also contain Y because of the third dependency, that is WZ determines Y. So I can have W, X, Y, Z, all 4 attributes. Now consider removing WZ determines X. So that means this dependency we are completely removing, and then trying to find out the closure of WZ, which would once again contain W and Z. And then using W and Z, now using the third dependency right here, once again, I can add Y to the list. And because of Y here, I can add X also to the list. So you see, even after removing this dependency, I am able to get my original closure of WZ. And that's why this X on the right-hand side is extraneous. But if you remove X from the right side, then the dependency itself becomes obsolete. There is nothing on the right side, so it's no longer a dependency. So you can go ahead and remove the whole dependency itself. So number 2 is going to be removed, and we're not going to use it anymore for any kind of calculation. So just be careful of that. Now we are going to talk about the third dependency. The third dependency is present right here, which is WZ determines Y. Remember, you don't have the second one now. And we are going to calculate WZ plus, which is equal to W and Z and Y. And once again, because of Y, we can, using 5, we can add X. So that is all right. Now try to find WZ plus without using WZ determines Y. In this case, we can add W, we can add Z, but then we have no way of adding either X or Y. So the closure is indeed changing, and that's why we cannot remove this functional dependency from our list of dependencies. Let's check the next one. Next one is Y determines W. So in this case, we are going to find closure of Y, which is Y comma W. And then because Y is present, I can add X from here, Z from number 6. So X and Z, and that means Y contains all attributes. Now let's try to find Y plus without the use of this dependency. I can add Y, and because of Y, using numbers 4, 5, and 6, I can add X, Z, and W. So once again, I'm getting all the attributes. So I don't need this W on the right side. And if I remove W from the right side, then there's no point in keeping the whole y determines w dependency at all. So that means this number 4 dependency is gone. Now the next thing we are checking is number 5, which is y determines x. And in this case, y plus closure is equal to y and x. And remember, number 4 is gone, 2 is gone. What can I add now? I can add z using number 6, and I can add w using number 1. So I'm getting all the attributes. Now let's calculate y plus without using y determines x, in which case I can add y, and because of y, using number 6, I can add z, but then that's as far as it goes. I cannot add x and w. So this dependency stays, I cannot remove it. And let's check y determines z. Here the closure of y is equal to y and z. And because y is present, I can add x using number 5 and w using number 1. So all the attributes are present. Now let's try to do y plus without this dependency number 6. Without that, if we do it, we can add y. Using number 5, we can add x. Using number 1, you can add a w. And there is no way to add z. So this is changing. These two are different. So we cannot remove this dependency. It is necessary. We keep it. So let's just write down the set of dependencies that we now have. The set now contains number 1, x determines w. Number 2 is gone. So number 3, wz determines y. Next one we have is y determines w is also gone. So we have y determines x. And we also have y determines z. And we are finished with the right side that we were talking about here. Now we are going to start and talk about the left side. So for the left-hand side, we are going to apply the second rule. And using that rule, first of all, we need to check now which of the dependencies is having more than one attribute on the left side, and that's only number 2. So we don't need to check 1, 3, and 4. We just need to check 2. So for number 2, we have wz determines y, and we need to determine if both w and z are absolutely necessary or not. To do that, we are going to calculate their closures. So the closure of w is w itself, and the closure of z is z itself. And now if you check, can you find y in the closures of either of these two? No. Y can be obtained only when w and z are combined together. If you use only one of them, you cannot get the attribute y. And that's why this dependency remains as it is. We cannot remove either w or z, because by using just w and just z, we cannot get y. So this set right here is our canonical cover, calculated from the original dependencies right here, which we converted into 6. So there are 6 dependencies actually present from where we reduced and made it to 4. So this is how you can calculate canonical cover or irreducible set using the extraneous attribute rules. And that's it for this video. I'll see you in the next one. Thank you for watching.